Hello, in this episode, we'll introduce several advanced type of guns. Okay. So the vanilla gun we saw can do a lot of amazing things, such as creating realistic fake images and such. So that technology has been improved, and here we first look at how people make improvements. So the first thing is that regularizing autoencoders. A classical unregularized autoencoder basically minimizes the reconstruction loss of the image X and the recreated image X had. So that process, there's nowhere where the latent space, the Z, the bottleneck, how it should be shaped. It just shapes as it wills. And the example from the data distribution, the map code scattered in the space. So it sits all over the place, and it's not necessarily best for the clustering purposes. So because there are no constraints, isn't it? So and you can sample codes that generate novel examples, and that's why we saw the variation of autoencoders are an approach to regularize the latent distribution through this Kuhlberg libel, the KL loss regularization. But here is another attempt, which is called adversarial autoencoder. The motivation is an approach to impose structure on the latent space of an autoencoder. And it's basically training an autoencoder with an adversarial loss to match the distribution of a latent space to an arbitrary prior. In some sense, it's adding the autoencoder with a discriminator that tries to wrangle the latent space into some arbitrary, whatever we will, kind of distribution. So can we use any prior? We can sample from either continuous or discrete distribution. So here's how it works. So here's the autoencoder. So here's an image, it enters the encoder, and it gets to a latent space C, and then back to a decoder to get the reconstruction. And the autoencoder basically tries to make this and this as close as possible, but nowhere this is constrained. But the adversarial autoencoder, here we have some distribution that we wish the latent space to look like. So this is what we want them to do. So what we do with this autoencoder is that we give this latent space, the true latent space distribution, and our arbitrary distribution that we want the latent space to look like. And we put it in a discriminator and have it trained. And what will happen eventually is that this will act like a generator in the sense that it will, because the goal is to make this Z, not only making the 2 and 2 hat, the X hat to be looking similar, but also the Z look as similar as possible to this P to fool the discriminator. Eventually, we are shaping the Z space like the space that we want the distribution to be. It's a pretty neat idea. So the reconstruction phase, first, we kind of try to minimize the reconstruction loss. But then there's the phase 2, where the Z and this, our arbitrary shaped Z, we want to fool the discriminator in such way that the Z space here will eventually mimic this space here. Okay. So if you look at VAE and AAE, basically VAE had the Kuhlberg libel divergence. This is basically replaced with the discrimination here, this fooling loss, isn't it? So why would you use an A instead of VAE? Well, the backprop through KL divergence, we must have access to functional form of the prior distribution PZ. And on AAE, we just need to be able to sample from a prior to induce the latent distribution to match the prior. That's one aspect of it. And here is an actual simulation out of it. So here are the bunch of digits, the MNIST handwritten digit data, and where they are clustered. In a VAE, they are here, they are reasonably clustered, but you can see it's not tightly packed, not some gaps here. With some nicely chosen prior distribution that we want the autoencoder to mimic, we can basically neatly wrangle this here. In fact, with an even smarter choice, we can actually make it act like this. So anyway, so there are many attempt of the prior distribution to cluster it in a more interesting way. So the pros of flexible approach to impose arbitrary distribution over latent space works with any distribution you can sample from, and does not require annealing or hyperparameters and these kind of things. But it's, of course, not easy to train a GAN for the autoencoder such. Here's another idea that people came about. It's called VAE-GAN. And what it does is that it combines an autoencoder with a discriminator. And what it does is that the two elements are the encoder and decoder. It tries to mimic the X and X here as close as possible. So this is a general VAE type of autoencoder. And then in the second phase, what we do is that, so here's a random number given and it tries to create an X, isn't it? It looks like a generator. So let's use it as a GAN. So using this decoder as a generator, then put here a discriminator, you can have here a GAN. So it's a VAE plus a GAN. So neat idea, isn't it? So these are two types. Of course, there are many more interesting types of GAN these days, but these are sort of some of the more advanced types of GANs that people have been developed. Thank you for watching this episode.